Assalamualaikum and greetings everyone. Today's topic is on scalar fields. Let's say you're given a scalar field phi. There are two partial derivatives that involve scalar field phi. Item 1 is gradients of scalar field and the second is directional derivatives. So today we're going to concentrate on the first item, which is gradients of scalar field. Now let's look at the definition of gradient of scalar field. Let's say you're given phi, which is a scalar function that is defined and differentiable in a region. Then the gradient of phi, written as grad phi, so we can use grad, G-R-A-D, that's short for gradient, is defined as, so you can write, you can denote gradient of phi as G-R-A-D phi, or you can use this notation, which is called del phi. So the gradient of phi or del phi is going to be a vector. So the gradient of a scalar function is going to be a vector where the x component would be partial phi partial x, and the y component would be the partial derivative of phi with respect to y, and the z component would be partial derivative of phi with respect to z. Okay, now let's concentrate on this symbol del here. So this symbol is called del, or in some books it's called nabla. It's a mathematical operator to which by itself it has no geometrical meaning. So in 2D, here you have partial dx, partial dy is waiting for something here. So by itself it has no meaning. But if you take the del of f, where f is a scalar, what you end up with is a vector where the x component is partial f partial x, y component is partial f partial y. So similarly in 3D, so let's say you have phi, which is a function, a scalar function in terms of x, y, and z, then the gradient of phi or del phi or nabla phi is going to be a vector where now your vector has three components. X component is partial phi partial x, y component is partial phi partial y, and the z component is partial phi partial z. Okay, now let's look at an example. So here in item 1, we're given f. As you can see, f is a scalar. It's equal to x squared plus y squared. Find the gradient of phi or del phi at point 02. And the second item is you're given a scalar function in terms of x, y, and z. Similarly, we are asked to find the gradient of phi or del phi at point 100. Okay, let's solve item 1. In item 1, we're given a scalar function f, x, y equals x squared plus y squared, and we are asked to find del f, or the gradient of f. So from the formula before, the gradient of f will give you a vector where the x component is partial f partial y, the y component, x component is partial f partial x, and the y component is partial f partial y. Okay, so this is our function f. Alright, so let's find the x component. So what you do is you differentiate f with respect to x. So that will give you 2x. And the y component, you differentiate f with respect to y. So you get 2yj. Okay, so now we want to find the gradient of f at a particular point. The point is at 02. So the gradient of f or del f at point 02 will give you, now you replace x with 0 and y with 2. So that will give you 0i. So because we have 2 times 0, that will give you 0, and 2 times y, in this case y is 2. So we have 4j. Okay. Alright, now I'm going to do a little sketching here so that we can understand what does the gradient of f or del of f mean. Okay, now at point 02, our scalar, our function, is equal to 0 plus 2 squared, which is 4, which means that what we have is x squared plus y squared equals 4. So at 02, at point 02, we have this equation, x squared plus y squared is equal to 4. And as you can see, this is an equation of a circle centering at x0, y0, and the radius is 2. Okay, if we plot this, okay, let's plot this circle. okay, on a xy plane. So let's say this is x-axis, this is y-axis. So this equation represents a circle of radius 2 centering at 0, 0. So definitely it will go through this point to this point, and here -2, and also this point -2. So we have a circle. So I'm going to sketch the circle of radius 2, centering at 0, 0. Okay, so here we have a circle of radius 2 centering at 0, 0. Okay, now let's look at our point 0, 2. This is our point 0, 2. So at point 0, 2, we are here. This is point 0, 2. And the gradient of f, this is the gradient of f, at point 0, 2 is 4j. So on this point, starting from this point, you move 4 units up. So because we have 0j, 0i plus 4j, so we have 1, 2, 3, 4. So now you have a vector. Okay, so we have a vector from point 0, 2 pointing upwards. Let me make it a bit thicker. Okay, so we have a vector from point 0, 2 pointing upwards like so. Okay, so this is the gradient of f at point 0, 2. So this is gradient of f at point 0, 2, which is equal to 4j. So from point 0, 2, you move 4 units upwards. Okay, what does it represent actually? Okay, so now let's look at our notes again. So this is the geometrical interpretation of del f, or the gradient of f. So scalar field fxy is a function of two variables given as z equals fxy. So geometrically, z equals a constant. So once you replace x with a value, y with a value, you get a value c here. So fxy equals c. So the gradient of fxy equals c is actually the normal vector to the level curve on the xy plane. Okay, so once you replace x and y with a value, you get a constant c. So then you have a function fxy equals a constant c. So if you plot this, what you have, what you're plotting is level curve on the xy plane. So the vector del f, or the gradient of f, is a normal vector at the point which is orthogonal to the tangent line of the level curve z equals fxy equals c. So now going back to our our example here. So at point 0, 2, we end up with this equation. Okay, at point 2 we have this x squared plus y squared equals 4. So when we plot that, we have a circle of radius 2. So this is what we call from chapter 1, this is level curve. Okay, so this is a level curve, should be in red there. So at point 0, 2, we have this point here. So the gradient of f at point 0, 2 represent the normal vector to the level curve at this point. So this is really the normal vector to the level curve at point 0, 2. Okay, so now let's say you change the point. All right, so let's say at point we want to know the gradient of f at point 2, 0. Okay, change it. The gradient of f at point 2, 0. So this is point 2, 0. Now the level curve is the one in red, the circle of radius 2, it's in red. So the normal vector to the curve would be pointing this way. Okay, that would be the normal vector. So if it's here, the normal vector would be pointing that way. If it's here, it's pointing that way. Okay, now that's the normal vector. So now let's look at point 0, 2. Sorry, 2, 0. So the gradient, or the del of f at point 2, 0. Okay, so this is the gradient of f at any point xy. Okay, so the gradient of f at point 20 will give you 2 times 2I plus 0j, okay, or it's just 4I. Okay, so 4I from this point 20, 4I, you need to move 4 units to the right. So we have 1, 2, 3, 4, and then you draw a vector. So that vector is the gradient of f at point 20, which is really the normal vector to the level curve. Okay, so the gradient of f is normal vector to the level curve. Now let's go back to the notes. So geometrical interpretation. So if you have f as a function of x and y, so when you replace x with x naught, y with y naught, you end up with an equation fxy equals a constant. And when you plot this, it's going to be a level curve on the xy plane. So the vector del f is the normal vector at point x naught, y naught to the level curve, which is really orthogonal to the tangent line of the level curve fxy equals c. Okay, so it's a normal vector to the level curve.